Kim Larsen from Aalborg, and with Maria Eichlseder also from Graz. So after an introduction, I will structure my talk into 3 parts. So I will talk about Englund's Elster first. Then I will adapt Elster to learning MDPs. For that, I will first assume exact information. So I will assume an ideal setting. And afterwards, I will adapt this to learning MTPs via sampling. So we do not have exact information, but we gain information via sampling of system traces. Okay, it's been a long week, so our motivation here is getting coffee. So here you see a Markov decision process that models a faulty coffee machine. So from state Q0 via coin, we go to state Q1, and here we see in curly braces the output beep, and that these outputs in curly braces label the states. And on the edges, we see inputs with corresponding probabilities. So with 0.8 probability with the but input, we get coffee. And with 0.2 probability, we reset the machine and get nothing. So we may ask ourselves, how likely is it that we get coffee in less than 5 steps? If we have such a model, this is easy, so we can simply ask Prism. Prism will tell us, okay, the probability is 0.96. Now the difficulty may be, what if the system is a black box? And this is actually what we will tackle here. So we will learn the internal structure of the system such that we can use Prism again and ask model checking queries. All right, how is this usually done? There's Alertia, which is a passive learning algorithm for stochastic regular languages. And this algorithm has been adapted by Mao and colleagues to IO Alertia for learning Markov decision processes. So this algorithm takes as input-output traces of the Markov decision process that we want to learn, and then it creates a tree from those traces. So here you see such a tree, and it looks quite similar to the MDP we've seen before. So we have outputs, we have inputs, and we have here frequency that denote how often a sample was present in the input sample. Now, given such a tree, we check between compatibility of nodes, and if they are compatible, if their subtrees are compatible, we will merge them. So here we would actually merge this right subtree into this left subtree into the right subtree, and with that merging we create an automaton. And after normalizing transition probabilities, we would get an MTP. So this is known as passive learning. In passive learning, we construct an automaton from a given predetermined data set, which could be system logs or some recorded test data. Active learning, on the other hand, which we will do, actively queries the system that we want to learn while constructing hypothesis automata. So the dataset generation is on the fly and could, for instance, be done via testing. Now, in passive learning, we place relatively few assumptions on the system's accessibility. So there simply needs to be some data that we can use for learning. But this also means that the models are only as good as the data. So if some behavior is not reflected in the data, it will not be reflected in the models as well. With active learning, we need to interact with the system, but this also means that we can steer the sampling towards regions that we want to cover. So we can steer the sampling such that we cover behavior that we are interested in. All right, now I want to quickly discuss Englund's Elster again. Probably can skip over that. We heard that. So we have a teacher and a learner, and they interact with each other via some queries here. So for the sake of completeness, there are membership queries. In these membership queries, we take strings over some alphabet, we give them to the teacher and ask, are those strings in the language? So we ask the teacher, is the empty string in the language? The teacher would respond here with yes. Is the string 0 in the language? Teacher would respond with no. And we do this until we can build a hypothesis. So we build some hypothesis automaton that is consistent with our information. And once we have such an hypothesis, we ask an equivalence query, so we give this hypothesis DFA to the teacher, and it will either respond with yes, you have the correct hypothesis, you have learned what you tried to learn, or it will respond with a counterexample to equivalence, which says that our hypothesis is not yet correct. So it's a string in the symmetric difference between the language that we wanted to learn and the language accepted by the hypothesis. Now, given such a counterexample, we integrate this into our knowledge, ask some new membership queries, and we iterate this loop until we arrive at a correct hypothesis after some further queries. All right, Englund's Elster uses observation tables. So we have those triples for storing the queried information. And we have rows labeled by a set S. This is a non-empty prefix-closed set of strings. So as we heard before, those strings are used to identify states in the hypothesis automata. Then we have rows labeled by one symbol extensions of the set S. And we have columns labeled by a set E, which is a non-empty suffix-closed set of strings. And the columns are basically used to tell the rows apart. The one symbol extensions are used to define transitions. Now the cells in the table store this mapping T, which basically records the membership query results in response to concatenations of row labels and column labels. To represent rows, we have an auxiliary function row, which represents the row contents in the tables. In order to derive hypotheses from observation tables, there are two well-formedness conditions that need to hold. The first one is closedness. So for closedness, there needs, for every one symbol extension of the set S, there needs to be a string in S such that the rows are equivalent. So this is necessary to create transitions in all states. And for consistency to hold, it needs to hold that for all pairs of equivalent rows labeled by S, their one symbol extensions need to be equivalent as well. So this is necessary to create deterministic hypothesis. And here you see an example of an observation table. So we have two rows labeled by the set S. So the empty string and A, the one symbol extensions, and we have columns for the empty string and the string A. And this would be the hypothesis constructed from the observation table. So you see the number of states is 2, so it's the number of non-equivalent rows labeled by S. And the transitions are actually created from the lower rows here, which are labeled by the one symbol extensions. Now let's move to the ideal setting where we assume exact information about the Markov decision processes that we want to learn. And here we also use a teacher and a learner. But now we learn deterministic MDPs rather than DFAs. Deterministic here basically means that every input-output trace that starts with an input, with an output and ends with an output is produced by at most one path. So we have, so for every trace, the state reached by the trace is uniquely defined. Now we have output distributions that replace the membership queries. For the output distribution queries, we give test sequences to the teacher. So these are sequences alternating between outputs and inputs, and that end with an input. And the teacher will respond with a distribution of outputs produced by the system in response to the last input. The equivalence queries are pretty similar. So for equivalence queries, we provide the teacher with a hypothesis Markov decision process, and it will either respond with yes or with a counterexample test sequence. And this test sequence basically induces different output distributions in the hypothesis and in the system that we want to learn. Now, for our Elster-based approach for MDPs, we also use observation tables. But now we store a prefix closed set of input-output traces to label rows. And we store input-output extensions of this set. So we use traces to identify states, basically. Then the set E is now a non-empty suffix-closed set of continuation sequences. So these are sequences starting with an input and ending with an input. So the concatenation of a row label and a column label is now a test sequence. So that we store, so we store in the cells the output distributions queried from the teacher. So the only thing that changed here is that we store output distributions. Or we store bottom, which denotes undefined behavior if we have a trace in the table that is not produced by the system. We again have the auxiliary function for rows. So we also adapted closeness and consistency. Now we require for all input-output extensions that there needs to be a non-extended row that is equivalent. And we require for all equivalent rows that their input-output extensions are equivalent as well. So this is also necessary to create edges in all states and to create deterministic MDPs. Here you see an example of an observation table. So we have rows labeled by traces. So we have outputs followed by inputs followed by outputs. And we have the set E consisting of the inputs. And we have output distributions in the table cells. From that, we can construct the faulty coffee machine. So as before, the number of non-equivalent rows labeled by S is the number of states, and the rows are used to create transitions in this hypothesis. Now let's consider the practical case where we gain information via sampling of system traces. So here we have again a teacher and a learner, but now the teacher interacts with the system under learning to sample traces via model-based testing. For that we need to be able to reset the system and to execute inputs on the system and to observe outputs such that we can learn from that. So we simply need to be able to sample traces. So we require two operations, a reset operation and a step operation. The teacher samples a multi-set of traces that grows during learning, and this is used for gaining output frequency information and for performing equivalence queries. The learner is able to query those output frequencies to estimate output distributions, and the learner stores them in observation tables again. And again, the learner performs equivalence queries. So we have three main queries. Now we have the refine query and the frequency queries that replace the output distribution queries. The refine query basically instructs the teacher to resample rarely observed traces to gain more accurate information about those traces. And we have the frequency query, which takes test sequences, and which returns output frequencies observed after those test sequences. For the equivalence queries, we either return a counterexample to approximate equivalence or none. Now we approximate equivalence queries via model-based testing, so we do not return yes, but rather we return none, denoting that we did not find a test sequence during testing. We again adapted the observation tables, so now they stayed pretty much the same as for the exact case, but now we map from row labels concatenated with column labels to output frequencies rather than to exact output distributions. So now, because we do not have exact distributions, we cannot check for row equivalence. So we need to statistically check for non-difference between rows. So we need to check for compatibility between rows. And basically, two rows are compatible if their cells are compatible, and two cells are compatible if their stored frequencies are not different. And we decide this based on the following criteria. So given two frequencies, such that they are not equal to 0 for at least one output, we say that they are statistically different if they do not have the same support, or they are too far apart from each other, which we decide based on a Höfting bound, which has also been used in passive automata learning by Carrasco and Oncina. Again, we adapted closeness and consistency. Here we simply plug in the compatible function. So here we require for all input-output extensions of strings in S that there needs to be a string in S that is compatible. And we, for consistency, require for all compatible rows that either their input-output extensions have not been observed, so we have no information about them, or they are compatible as well. Now, for the hypothesis construction, we face a problem because compatible is not an equivalence relation. So before we could use row equivalence to partition the set S and create one state per equivalence class. Now we do something similar, so we partition S based on compatible, but we choose a representative of each block based on frequencies. So we choose as representative of a block in a partition based on how often we've seen it. And we ensure that for each trace in a block that each trace is compatible to its representative, but the traces in a block may not be pairwise compatible. Finally, we create a state for each representative, so for each block. And we estimate transition probabilities from observed frequencies that are stored in the observation table. And in case of low information for some successor state, we move to a special sync state that has an output label that is not in our original output set. Now, finally, we want to discuss the teacher implementation. So as I said before, the teacher samples a multiset of traces, and this multiset grows during learning. And it grows in response to two queries. So in response to refined queries, so here the teacher takes an observation table, and the teacher selects rare sequences from the observation table. So, and this is decided simply based on a threshold. So if a test sequence has been observed less than k times, we consider it rare. Then we try to resample those rare traces by first creating a prefix tree from the rare traces and testing the system under learning with the goal of reaching a leaf. By that, we sample new traces and add them to our multi-set of traces. For the equivalence queries, we are given a hypothesis and we apply two strategies. So first, we perform model-based testing of the hypothesis structure. So in that kind of testing, we try to find a trace that can be observed on the system, but not on the hypothesis. So this would be a counterexample to the structure of the hypothesis. If we do not find such a counterexample, we check for compatibility between the multiset of traces and between the hypothesis. For that, we select all non-rare test sequences that we observed so far. So these are made up of a single trace and a single input. And first we check if the trace is observable on the hypothesis. If it is not, then it is a counterexample because it has been observed before. Otherwise, we determine the state reached by the trace and determine its representative, and we check for compatibility between the representative concatenated with the input I and the trace concatenated with the input I. And if they are not compatible, we found an approximate counterexample to equivalence, and we added to our observation table. All right, now I want to discuss some experiments that we performed. So for the experiments, we took known MDPs, but we sampled traces from them. So we basically treated them as black boxes during learning, but we took known MDPs to be able to measure how good our learned models are. We learned models with our sampling-based Elster approach and with Eichlseder. And we configured both approaches such that they learn approximately from the same amount of data. To measure how close we are to the true model, we computed the discounted bisimilarity distance to the known true model. And we performed model checking queries on the learned and the true model and computed the difference between the true results and the estimated results from the learned models. And we also measured the learning runtime and the model size of the learned models. So here you see a first grid world example that we used for our evaluation. So we have an initial location and a goal location. It can be modeled using 35 states. And so what you here see is the number of sampled traces and the number of sampled outputs. So you see indeed both learn from the same amount of data approximately, but our approach required much more time, but still less than 2 minutes. But here you see, if we look at the discounted bisimilarity distance, this increased learning runtime really pays off. So this is a value between 0 and 1, and the lower value means a closer model to the true model. So our model is much closer to the true model. So model checking results can be expected to be more accurate. And this is actually what we see here. So we checked for reachability of the goal location with varying number of steps. And we see that the model checking results for our Elster-based approach are pretty close to the true results, whereas the Eichlseder results are quite far apart from the true results. And this can be explained by, for instance, considering the system size. So here you see we learned a model with the exact number of states as the true system, while the Eichlseder model was much smaller. So the structure of our model was pretty close to the true model. We evaluate on a second grid world, which is approximately double the size. And here you also see that the bisimilarity distance for our Elster-based model is much smaller than for the Eichlseder model. And also the model checking results are pretty close to the true results for our Elster-based approach. And we again see that we learned a model with the exact same number of states as the true model. So if you're interested, we have an extended preprint on arXiv. There we discuss further experiments with a consensus protocol with 272 states and with a slot machine example with 109 states where we also perform model checking queries and compute bisimilarity distances. So to sum up, I described an exact Elster-based learning approach for MDPs, and we used that as a basis to develop a sampling-based Elster-style learning algorithm for MDPs that can be implemented solely via testing. We've seen in the experiments that active test-based learning is effective for stochastic behavior, so we created accurate models. And actually for our grid worlds, the probability estimations from model checking those learned models were within 0.02 of the true probabilities. So with that, our Elster for MDPs enables probabilistic black box verification of, for instance, stochastic protocols or uncertain behavior in general. Thank you.